Hello, welcome back to physics. We're going over inclined planes. And what we're doing now in inclined planes is last time we talked we had an inclined plane and we had a mass, and this was no friction. This is a frictionless surface right here. So without any friction, this block would normally just slide on down that inclined plane. And that's what we calculated last time. We calculated all the forces acting on this mass 1 right here. And we calculated then what the acceleration of the block would be down the incline. Today what we're going to do is something else special. Today we have a massless string that is going to go up and over this frictionless pulley, of course. And on the end of that string is hanging a second mass. Okay? Now, mass number 1 has a mass of 20 kilograms. Mass number 2, we're going to have 15 kilograms. And our inclined plane here is at 35 degrees. So now what we want to do is answer the exact same question. What is the acceleration of mass number 1 going to be? With this mass hanging over here, 15 kilograms, is that going to be enough to make our mass slide up the incline? Or is mass 1's parallel force pulling down the incline going to be strong enough to pull both of these down? This one pulling down and lift up on mass number 2. So that's what we're going to do. So to start things off with, we're going to do exactly the same we did on the beginning inclined plane videos. If you don't know what that is, of course follow along. We're going to go through the exact same process, or you can refer back to those other videos if you wish. Yeah, let me get my pen here. Now, what we're going to be doing is, get the pen here, sorry. The first of all, let's talk about the weight and the forces acting on mass 1. Okay, that's really what we're asking about. So on mass 1, the only force acting on it is, of course, gravity, which is going to pull straight down on that mass. Okay, remember, weight or gravity always pulls straight down. Doesn't matter what angle the ground is at, mass always pulls straight down. The only exception to that rule is if you're anywhere near a big, huge mountain. Believe it or not, they've actually shown where the mass gravity actually pulls a little bit over to the side because of that big massive mountain. But today we're just going to talk about the weight pulling straight down. So let's do that. And of course, there is going to be another mass pulling on this block right here. We'll talk about that later. And that is through the string, through the tension force of that string, pulling down on mass number 2. All right, so our first vector we want to put in here is for the weight for mass 1, which is going to pull straight on down there like that. And we make that into a vector. And remember, you want to make this vector nice and long because it's going to break up into 2 smaller components, and it makes it really difficult to find your triangles and find your angles properly if you don't make that force of weight long enough on the vector. So force of weight, and don't forget we always like to put down m times g. And since we've got 2 masses, you got a mass 1 and we have a mass 2, we better make sure we know which mass we're talking about down here. So we're talking about mass 1 right here. So we're going to actually have 2 weights. We're going to have a weight for mass 1 and we're going to have a weight for mass 2. So we're going to put a little 1 right there so we don't get these 2 weights confused. All right, next thing that happens is because of that inclined plane, this the weight right here is going to actually get split and pull partially down the inclined plane, and it partially pulls directly 90 degrees right down into the surface of the inclined plane. So let's draw those 2 vectors in. Now part of this force of weight right here is going to pull that mass down the incline this way. And we'll turn that into a vector. And the way I know how long to make that vector is if you go 90 degrees to that surface of that incline, then it should get pretty close to making a really nice 90-degree angle triangle right there. Okay? And this is your force parallel. It looks like an 11, but that's a symbol in mathematics for parallel. Next one we want to draw is our force perpendicular. It's the force that goes straight into 90 degrees, right into the surface of the inclined plane. And that force vector is right about there. Okay? Again, how long do I make that? I make that so that parallel to that inclined plane, it should make a pretty nice right-hand triangle, a right triangle right there. Okay? So the whole thing makes a really nice rectangle, pretty squared up. Okay? It helps to have a protractor to do all this. And this one is going to be your force perpendicular. Okay? The force perpendicular. Now, remember last time we did this video, we used our trigonometric functions to be able to find the force parallel and the force perpendicular. But before we did that, we have to figure out these angles in here. Inside these two triangles right here, we have to figure out the angles. And these two triangles right here, they look very similar to the big inclined plane triangle with this 35 degree, and they are. These two triangles are what's called a similar triangle, which means they have the same interior angles, but the lengths of the sides are different, so it's all proportional. So this narrow little angle right here, you can probably see on this triangle right here, that is going to be this little angle right here. So this is 35 degrees. And that's going to be the same up here. That's going to be 35 degrees. Okay, I know I wrote those kind of small in there. I don't want to garble this up with too much stuff. Alright, so now let's figure out this calculation. So we're going to find the force parallel. Okay, the force parallel. So in our force parallel right there, we are trying to find that length of the triangle right there, and we know this angle right here, and in a minute we're going to know this big long hypotenuse right here. So let's do that calculation for the hypotenuse first. So force of weight 1 is going to be the mass times gravity. So force weight 1. Remember, always show all your work so you remember later how you got those numbers. Mass 1 is 20 kilograms. That's 20 times gravity, which is 9.8. So force of weight 1 is going to be, I believe that's 196. 196, and the units for force comes in newtons. Okay? So now we know this force of weight right here is 196 newtons. So now, what do we know about our triangle? We know that we're trying to find this force parallel right here, and we know this angle right here. We know the hypotenuse is 196. So, if you look at this triangle, remember we choose the corner we're working from, that's 35 degrees. And we're looking for the side that is directly across from it. So that is the opposite. And we know the big long side here, which is the hypotenuse. So the trigonometric function that has opposite and hypotenuse is sine. So we write down that trigonometric function. The sine of the angle is the opposite, which is going to be force parallel, over the hypotenuse, which is 196. So now let's plug in the rest of the numbers. Oops, I wrote in 30. Excuse me. Sine of 35 degrees is equal to force parallel over 196. Bring the 196 over here. And our force parallel is going to be 112. newtons. Okay, so our force parallel right here is going to be 112 newtons. Now let's find the force perpendicular. The force perpendicular over here, we have to look at this triangle. We know that this is 35 degrees, so we are looking for the side that's right alongside that angle that we chose. So that means that this is the adjacent side. If it's the one next to it, it's the adjacent. And again, we know the big long hypotenuse. So adjacent and hypotenuse would be cosine. So the cosine of an angle is the adjacent over the hypotenuse. So cosine 35 degrees is the adjacent, which is the force perpendicular, or the hypotenuse, which is 196. I'm going to skip a step since you all know your algebra. It's going to be 196 times the cosine of 35 degrees, which is going to be 161. Okay, hopefully everybody can see that. So now we just figured out that this is 161 newtons. All right, we're getting all of our components. We've found all of our different components there. So now it's time to do the sum of the forces. We've got all the forces outlined on here, so now we can try and figure out what forces are acting on this block, and then whatever net force is left over, from that we can find out what the acceleration is going to be. But now we got to look at something else. We have this additional force up here from this tension force of this string right here going up and over that frictionless pulley, and now we have this weight pulling down over here for mass 2. So we should, since this is going to be a force right here, we should calculate the force of weight on mass number 2, which is going to be the mass 2 times gravity. So force of weight 2 is mass 2, which is 15, times gravity, and force weight 2 is going to be 147. Okay, now we know all the forces. So now we can do our sum of forces. Now, the next thing, remember our 7-step process. We have labeled all of our forces acting on our object, mass 1. We have now labeled them, we have defined them all, drawn the vectors in, and then the next step is, excuse me, we have to find what those components are, and we did that. We calculated all the components. Next step is to find out what's positive, negative. So I'm going to draw a little tiny Cartesian coordinate system here, and we're going to decide, I'm going to keep to the normal standard. To the right will be positive, to the left will be negative, up is positive, down is negative. Okay, now we can do our sum of all the forces acting along the line of motion. That line of motion, of course, is right alongside this inclined plane right here, right along the surface. So we are going to call that the x direction. Okay, so we're going to do a sum of the forces in the x direction. Well, the one force acting on this thing for sure along the surface is that force parallel right there, and it's acting in the positive direction. So it's force parallel plus any other forces acting on it. The only other force is this tension force right here pulling from the string, which is caused by the force of weight number 2. So force of weight of 2. And that force, since it's going up this way, is going to be negative. So it's plus a negative force of weight number 2. Now let's plug in some numbers. Sum of the forces in the x direction. The force parallel is 112 plus a negative 147. Okay? Now, the next step in finding the forces is we have to ask ourselves, is this object going to accelerate? Well, remember, that's what we're trying to solve for. What is the acceleration of that box going to be? So yes, the answer is yes. And when that's true, that means that your sum of forces is actually, don't forget, that is your net force. And according to Newton's second law, net force is mass times acceleration. That's according to the second law. So what we're going to do is substitute mass times acceleration into the sum of the force right there. So instead of sum of the forces, we're going to put in mass times acceleration. And that's all equal to 112 plus 147, which actually comes out to be negative 35. Now, we're almost done here. We're almost going to find that acceleration. Now, this mass right here, are they talking about the mass of 1? Or are we talking about the mass of 2? Well, remember, we have to ask ourselves, what exactly is being accelerated? There is a net force of negative 35 newtons, which is doing what? It's supposed to be accelerating this mass right here, mass 1. But mass 1 is connected to mass number 2. So whatever net force is acting on this mass right here, because mass 2 is connected to it, it's going to have to accelerate both of them because they're attached together. So this mass right here is actually mass 1 plus mass 2. So let's plug in those numbers. Mass 1 is 20 kilograms plus mass 2, which is 15. Now we add those two together. And I promise you, I did not work it out this way in advance. This is just totally weird. So acceleration is going to be negative 35 divided by 35, which I'm pretty sure we all know what that's going to be. That's going to be 1. And the units for acceleration is meters per second squared, or meters per second. And of course, negative. Can't forget that negative on there. Now remember, we're good physicists here. So we have to ask the question, go back, look at the problem. Does negative 1 make sense? So let's take a look. Here's our Cartesian coordinate system. And it says we're going to go in the negative direction. It says this block right here is going to accelerate in the negative direction. So that means it's going to get pulled up the incline. So this M2, even though it's only 15, it's stronger than that force parallel. So the block is going to accelerate up the incline, which is the negative direction. And there, we're done.